Solving systems of equations in three variables. From your geometry course, you may remember drawing, graphing, and/or writing equations for planes. Equations for planes, when drawn three-dimensionally, can involve three variables and introduce what's known as the z-axis. So we have our typical xy plane, but then we also have the z-axis, which is three-dimensional. So it's coming out of the page and then going into the page. That's why we have this dotted line there. This is called the z-axis. When we have three planes, there are multiple scenarios for how they will intersect, if at all. We could have infinite solutions where the three planes intersect one another in a line. We could have one solution where they intersect at a point. You could think of the one solution point as a corner from any room, like where the front wall, side wall, and ceiling meet one another. They could also have no solutions where the three planes are parallel to one another. In this section, we will focus on the second scenario of a single solution to the system. In other words, we're finding the point where three planes intersect, or the corner of the room. We will apply our knowledge of solving using elimination and substitution to calculate this solution. The same strategies will apply to solving these systems. It's worth noting that because we have three unknown variables, we need three distinct equations in order to find the solution. So here's an example. 3x minus y plus 4z is equal to negative 5. 6x minus y plus 3z is equal to negative 9. And 5x plus 5y minus 5z is equal to 20. Let's work through finding the solution to this system of three variable equations. One effective strategy is to pair up equations and eliminate the same variable in both. And as a result, you will need to use one equation twice. This will result in a system with two variables, as we are used to solving. So let's begin by looking at all three equations that we have. We have a minus y, a minus y. Okay, if I pair these first two up and I multiply one of these equations by negative 1, the y's will cancel. And then if I do, say, this last one with either of these and multiply the equation by 5, the y's will also cancel. So let's use the second and third as one set and the first and second as the other set. So if I use the second and third in my first set, we're going to have 6x minus y plus 3z equals negative 9, and 5x plus 5y minus 5z is equal to 20. If we multiply our first equation in this system by a positive 5, we will end up getting 30x minus 5y plus 15z is equal to negative 45. And then the second equation, or our last equation that we used, second in this set of two, will remain the same. And then if we add straight down, we'll get 35x, the y's cancel out, plus 10z is equal to negative 25. And again, if we use our first two paired together and multiply the first one by negative 1, keeping the second one the same, we will end up having negative 3x plus y minus 4z is equal to positive 5. And we'll keep the second one the same here. 6x minus y plus 3z is equal to negative 9. Add straight down, the y's cancel out. We'll be left with 3x minus z is equal to negative 4. Continuing with the two resulting equations, we must then choose a new variable to eliminate. So we had 35x plus 10z is equal to negative 25, and we had 3x minus z is equal to negative 4. Well, since the signs of z are opposite, and one of the coefficients of z is negative 1, it's easiest to get rid of z by multiplying everything in the second equation by 10. And keeping the first equation the same. So we'll have 35x plus 10z equals negative 25, but then we'll have 30x minus 10z is equal to negative 40. after we distribute the 10 through. Then if we add straight down, we'll end up getting 65x, the z's go away, is equal to negative 65. And then if we divide both sides by 65, we get that x is negative 1. Now that we have one variable, we can substitute this value of negative 1 in for x and solve for the other two. So if we take the x value of negative 1 and substitute it into 3x minus z equals negative 4, we can then solve for z very quickly. So we'll end up getting negative 3 minus z is equal to negative 4. If you add 3 to the other side, you'll end up getting negative z is equal to negative 1, so z is going to be positive 1. Now we can take both x and z and substitute them into any of our equations that we have here. Let's use the first one. So 3 times negative 1 minus y plus 4 times 1 is equal to negative 5. We'll have negative 3 minus y plus 4 is equal to negative 5. So negative 3 plus 4 is positive 1. So 1 minus y is equal to negative 5. If you subtract 1 from both sides, you'll get that negative y is equal to negative 6. Therefore, our y value is going to be positive 6. And then we can list each variable separately or express our answer as a point. And when you express points in a three-dimensional plane, it goes x comma y comma z. So instead of just having a pair of numbers, now we have 3 of them. So we're going to have negative 1, 6, and positive 1 as our point of intersection for these 3 planes. Here's an activity. Choose one of the ordered triplet solutions from below and create at least 2 different systems of 3 equations that have that solution. And once a system is created, you could have someone check that it does, in fact, have the correct solution. So here's an example of what can be done. And I'm going to select this point, 3, 1/2, 0. And here's one system that I think will work. X plus 2y minus z is equal to 4. Then we have negative x plus 2y plus 2z equals negative 2. And the final equation in this system is 3x minus 2y plus z is equal to 8. Okay, so I'm going to solve it by pairing the top 2 together and then the bottom 2 together. And I'm going to get rid of y in both cases. So the first 2, we have x plus 2y minus z equals 4. And I'm going to multiply this bottom equation of this set by negative 1 so that my 2 y's cancel out. So I have negative x plus 2y plus 2z equals negative 2, and I'm multiplying this whole thing by negative 1. So I'm going to distribute it through. And then the first equation is going to stay the same. X plus 2y minus z equals 4. But then I'm going to have a positive x, a minus 2y, and a minus 2z equals positive 2. And then if we add these together, 2 y's cancel out. We have 2x minus 3z is equal to 6. Okay. Now we're going to take the bottom 2 equations, and you actually don't have to multiply them by anything. The 2 y's cancel out automatically. So I'm just going to rewrite them. And that will be negative x plus 2y plus 2z is equal to negative 2. And then we have 3x minus 2y plus z is equal to 8. And then we'll have 2x plus 3z is equal to 6. And now we're going to take this equation and put it below this one. So 2x plus 3z equals 6. Hey, that's pretty cool. The z's automatically cancel out. So I have 4x is equal to 12, making x be 3. Okay, so far that works. Now let's substitute our x value into one of these equations and solve for z. So I'll do 2 times 3 plus 3z is equal to 6. So 6 plus 3z is equal to 6. 3z is equal to 0, so z is equal to 0. Okay, that one works too. Now we've got to solve for y. And all of these have a 2y in them. Okay, so let's use the first one. So x is 3 plus 2y minus 0 is equal to 4. If I subtract 3 from both sides, we'll have that 2y is equal to 1. So therefore, y does indeed equal 1/2. So we do have all of our coordinates from this one point and a system that is valid for them. Try creating another system for this point, or choose another point and create another system of equations that will satisfy that point.